Hello everyone. In this video, I will summarize our main work and the steps that we took in completing our capstone design project. For our project, we wanted to design a small-scale vertical axis wind turbine, which is a device that converts energy from the wind, a free, renewable and green natural resource, into kinetic energy, which is then converted to electrical energy. There are two orientations of wind turbine, which are the horizontal axis wind turbine and vertical axis wind turbine. Horizontal axis wind turbine have their rotating axis parallel to the ground. The generator and rotor are located at the top and must be pointed at the wind. The turbine can also be moved by a servo motor attached to a wind sensor. Vertical axis wind turbines have their rotating axis normal to the ground. They can be placed on rooftops or on the ground and can collect the wind energy from all directions. They are also much more compact and take up less space than a horizontal axis turbine. They are mainly used at slower wind speeds and lower altitudes, where less wind energy is available. Due to the location of the rotating axis, the generator can be simply placed at the ground, making them easily accessible. For our project, we chose the H Darius type because it is suited for lower wind speeds of the UAE. It also works in all directions and is less complex to design. The main objective of our project is to find the optimum blade height, rotor radius, number of blades, airfoil chord length, and airfoil type for a small-scale vertical axis wind turbine, using an analytical approach and equations in order to find the design for providing the maximum allowable power. In order to find which design will give us the maximum power, we must analyze its power coefficient, which we will refer to as CP. In order to find the optimal design, we will be using QBlade, which is an open source software developed by the Technical University of Berlin. The model used for aerodynamic analysis by the software is the double multiple stream tube with variable interference factor, regularly referred to as DMSV, which is enclosed in the momentum models category and is based on the conservation of momentum principle, which can be obtained from the Newton's second law of motion. It has been used successfully to predict overall torque and push loads on a Darius rotor. The model uses the actuator disk theory two times, one for the upstream and one for the downstream parts of the rotor. This theory represents the turbine as a disk which creates a discontinuity of pressure in the stream tube of air flowing through it. The pressure discontinuity causes a deceleration of the wind, which results in an induced velocity. The cleared volume of the rotor is divided into adjacent aerodynamically independent stream tubes. Each is recognized by its center theta point, which is characterized as the angle between the direction of the free stream velocity and the position of the stream tube in the rotor. This graph was obtained using the QBlade software. In the x-axis we have TSR, which is the tip speed ratio. It is a ratio between the tangential speed of the foil tip and the speed of the wind. The y-axis contains the CP, which is the power coefficient. We must maximize this value for our range in order to find the best design that will give us the best power production. The data shows us that this design would give us the best power compared to other designs for the wind speed here in the UAE. We used 3 blades instead of 4 because it would be easier to manufacture and it can remain operational in higher wind speeds without stalling or failing. This table shows the results for the optimum design that we have found using the software, as well as the parameters that we have calculated, such as the power from the wind and the expected power that can be obtained with the turbine. After we chose our design, we decided to create a 3D model using SolidWorks. After we made this model, we were able to run simulations on it to find values such as the torque, which was 14 Newton meter, as well as how the model will rotate at our wind speed. In conclusion, we found that the vertical axis wind turbine is suitable for the UAE and can be used to produce power. The size of the turbine must be small and it must use high blades in order to produce more power. We recommend that another group build the turbine using the design we obtained from our calculations to confirm our results.